Hello, everyone. In this video, I will be going over the common fate growth model. The common fate growth model, for those of you who are unfamiliar, is examining change at the dyad level. So the common fate growth model will differ from the dyadic growth curve, where you're kind of estimating dyad member one and dyad member two growth or rate of change over time, but it's done at the individual level. And of course, the non-independence is accounted for by correlating the residuals of the observed variables. But in the common fate growth model, what we are actually doing is we are estimating what is shared between partners and examining changes in the whatever is shared between partners on that construct. So we could look at changes in dyad level, relationship quality, or dyadic coping, or support, or strain, or any other kind of variables that would kind of qualify for a common fate analysis. And so the first thing we'll do is kind of take a brief picture and a brief moment and look at kind of what the visual representation of the common fate growth model is. And so this is a representation of the common fate growth model. And as you can see here, it looks identical in a lot of ways to a traditional growth model. One of the primary differences is, however, is that we are going to be using latent variables. As you can see, time one, time two, and time three are all latent variables indicated by, in this example, mothers and fathers report on a construct. So this is also called a curve of factors model. So we are estimating a latent growth curve, the intercept and the slope, but we have factors as indicators rather than observed variables like we would have in many other growth curve analyses. And so each of these time points is actually a common fate variable and of the same construct over time. So in our syntax, we'll be going over male and female support using 4 waves of data, as you can see here. And so we will have time one, time two, time three, and then probably a time four out here to the right. And so what we'll do is, just as in any traditional growth curve model, is we will we will create an intercept factor and fix all of the loadings to be one, which means the intercept equally indicates or accounts for variance at time one, time two, time three, and time four. Likewise, with the slope factor compared to other growth curve analyses, we are going to fix the loadings of those in accordance with time, with the time between waves. So in the data we are using, everything is gathered roughly annually. So we'll just use 0, 1, 2 in this diagram, and then we'll add a 3 in the common fate growth curve analysis that we are going to run. So in that way, everything is almost identical to again the dyadic growth curve or just your traditional latent growth curve model within a structural equation modeling framework. One of again the Now we're going to kind of shift to the differences. Is now that we have latent factors as indicators, it creates a little bit more complexity. But within the common fate model, it's actually not too difficult. And so, like the traditional common fate model, we're going to fix all of our loadings to be one. All right. And so, and essentially that means they're also going to be constrained to equality, which is why you see lambda one on all of the loadings. Right. And so again, that's very traditional, very common fate. And so if you're not familiar with the common fate model, I have other videos that go over the common fate model, and watching those and learning how to run those analyses will be helpful before you are become acquainted with estimating growth or rates of change in those constructs. But everything is constrained to one, as in the traditional common fate model. And then we covary all of the father's reports with one another, and we covary all of the mother's reports for one another. This is kind of a within person kind of covariance to account for common factors that are unmeasured in the model that might be influencing um, the father's report at time one, time two, time three, time four, and so on. Likewise, we do the same thing for the mother, right? And so we don't we won't correlate the mother's reports with the father's for a couple of reasons. One, if you covary mother and father's reports, that can create statistical identification issues, both empirical under identification, and you can also run into estimation errors, particularly if you are just estimating one common fate variable, you would actually have a -1 degree of freedom. So that can cause, again, some significant problems. And essentially, what we are kind of assuming about between the mother and father is that all of the information about mothers and fathers in relation to the construct of interest, perhaps its support, is actually located in the time one variable. So if there's an unmeasured common cause of support, again, that can lead to pretty substantial issues in the interpretation of our latent variable, but also again in that estimation. So again, that's again one of the reasons that we would not estimate residual covariances within partner or across partner, so mothers and fathers. Um, uh, Another way of kind of saying that is that we assume that all of the information that is shared between mothers and fathers is actually located in that latent variable. And, and so if you recall in kind of latent growth curve modeling, especially if you use the growth function within lavaan, we will be demonstrating this within lavaan using the sum function. But if you use the growth function in lavaan, one of the things that it does is it constrains your item intercepts to be 0. And what that does is that pushes information about the means into the latent space. So you have item intercepts for mothers and fathers, and by constraining those to be 0, is you are pushing that mean back down this arrow, and you are now freely estimating a mean in the at the latent level or in the latent variable. If you recall and think back to like measurement invariance, we generally set that factor mean either to be 0, or we use one of the indicators that using the marker method to kind of scale that latent factor. And so that's what we actually need to do here is we actually need to scale this latent factor and push the mean information from these observed variables up into these the latent variables, right? Because again, we are interested in latent means, right? So our slope is a mean and our intercept is a mean. And so therefore we can't just fix it to 1. If we were to fix the mean to 1, that means we are saying the slope is 1. And so that means the rate of change in the variable over time is 1. And that might actually be an incredibly terrible fit to the data. So in other words, we are kind of imposing what the rate of change is by setting the scale of the latent variable to 1, for example. Right. So we actually need to give the latent variable some information. And so how we do that within the common fate growth model is that we're going to fix one partner's, it could be the mother or the father, does not matter, it's arbitrary. We're going to fix their item intercept to be 0. So what that is doing is that's pushing this latent mean, so information about the mean of the observed indicator, back down this arrow, back up to time 1, and that same thing is happening at time 2, and that same thing is happening at time 3. So that's all well and good, right? So we are now, because we're concerned with latent means, we're getting information kind of where it needs to go in a way, and kind of. Uh, we care about the latent means, but at the intercept in the slope level. So now we have three latent variables, time 1, time 2, time 3, that all have information around means. It's scaled. But what happens here is because we have latent indicators, is we now need to push the mean information from the latent indicator up to the intercept and up to the slope, back down these regression lines, right? And so the way we are going to do that is kind of very similar to what we do with them in this example, the mother's intercept. We are going to set the means of time one, time two, time three, time four, and all of the common fate factors. You know, you could have 10 waves of common fate variables, time one through time 10. All of them are going to be set to zero. So what that is doing now is this exact same process as before. We are now pushing the late information about the latent mean that's located at time one, time two, time three, and time four up to the intercept, and where it's in the certain amount of information that's going to be transported to the intercept is going to be based on these factor loadings. And the amount of information that's going to be transferred to the slope is going to be based on these factor loadings, 0, 1, 2 for the slope and 1, 1, 1 for the intercept. And so that is how we capture a linear rate of change in this example using three waves of data. Because in three waves of data, just like the latent growth curve and dyadic growth curve, you can only estimate linear change, right? Another thing that I will mention is even though we are setting the mother's intercept, the observed variable intercept to be zero, we are freely estimating the father's, but the father's intercept is constrained to be equal across all times. So you can see tau 1 here. It's freely loaded, indicated by that asterisk, but it has A1 has that label to indicate that it's constrained to equality across these three time points. All right. And so again, that's going to be the basic formulation for the common fate growth model. And of course, you know, if you have four waves of data, you can do quadratic and you can do other things. You can use uh, predictors to account for variance in the intercept and slope. You can estimate a distal outcome where you have the intercept and slope predict, you know, let's say likelihood of divorce if we're using support. So changes in dyad level support can be used to predict whether or not the couple divorces. Right? So you can there's a lot of flexibility in what we can do within a structural equation modeling framework. So let's go over to lavaan. And what we will do is we will first, you know, set our working directory. And so we'll go in, we'll set our working directory. This happens to be my working directory, so it's already set to the correct folder, but you might need to go find your folder where your data file and your syntax file are. Once you have your working directory set, you can create load your libraries or your packages, I should say. And I'm using Haven and lavaan. And then I create my data object, and here's my SPSS file, and that's me using the Haven package to import that SPSS data. All right, and so we will first estimate the unconditional common fate growth curve model. So the unconditional common fate growth curve model is exactly kind of what you would think is the growth or the rate of change, that slope factor, isn't conditioned on anything else. We are simply investigating whether or not there is a rate of change because we are freely estimating the mean of that latent variable. We are also going to get a variance attached with that. So there are going to be person-to-person differences in our model in relation to their slopes. People are going to change at potentially different rates. All right. And so we just want to see, is the slope of the sample on average different from zero? And is there variability in that sample? You know, because it might be that there's the slope is significantly different from zero, but there's no variability, which means that the slope is essentially a constant, which means it's going to be exceptionally hard to predict, right? If there's very little variance, and it's going to be exceptionally hard to use that to predict something else because, again, there's going to be very little variance. So we will first start off by specifying our four common fate latent variables. And so we are using um, uh, marital support as our construct that we are going to investigate change in. So these variables are from the pair fame data, and so These are actually not the best common fate variables, these male and female support. They would actually be more partner referential items rather than relationship referential item, which you want within when you're doing common fates. But I am using them more for illustrative purposes here. And so what we're going to do is we're going to have support at time one, time two, time three, and time four. Or I guess time two, time three, time four, time five. If we're going by the pair fam data kind of waves, or one, two, three, four, if we are just using kind of just general notation for longitudinal data. All right. So we are going to include 1 star in front of all of the factor loadings. This is what constrains them to be 1. More specifically, it constrains the unstandardized loadings to be 1. So here in our intercept, this is our latent factor. So you specify latent factor via equal tilde. You see I did that above as well. And we do our intercept, just as you saw in the diagram, you constrain the factor loading to be 1 across all waves, right? And so you then specify the slope starting with 0, and then you do 1, 2, and 3 because we are estimating linear change, and our waves are equally spaced approximately 1 year apart. So by specifying the model like this, specifying the slope in the intercept like this, this allows us to actually make the intercept latent factor easily interpretable. All right, so with this specification, the intercept is interpreted as the couple's level of support at time 2, or at the initial wave, all right, at this first wave of data collection, right? So technically, you could fix these variables to really whatever you want. It could be, 100, and you could do 100 and 101, 102. You kind of get the point. But with this type of specification, again, the intercept becomes a little bit more interpretable. All right, so here I'm just specifying syntax to estimate the means, the variances of the slope and the intercept factor. So we have I tilde tilde I, that's estimating the variance. So S tilde tilde, that's estimating the variance of both the intercept and the slope factor. And then we have a single tilde with 1 that is specifying a mean, within lavaan. So as I said, when I was talking with and referencing the diagram, we are fixing the latent means of the common fate variables to be 0. And so the way you do that in lavaan is up here you saw that we have the I tilde 1 to represent a mean. We do the same thing down here, but we have our latent variable, we have a regression coefficient, but then we have a 0 in front of that 1, and that tells lavaan to constrain that mean, the intercept, to be 0. Okay. So just like the traditional common fate model, we are correlating the residuals of all the male variables together, and we're going to correlate the residuals of all the female variables together. And what we are going to do here, this is the fixing the intercepts to be equal and to be 0 for each dyad member. So in this example, we are fixing the male intercepts for their reports on support at wave 2, 3, and 4, and 5 to be 0. Right. So again, that's what's pushing mean information up to the common fate variables, right? That these guys up here, and then this syntax is pushing that that mean information that's been transmitted up from the observed indicators now into the slope and the intercept factors. All right. And so for females, we are estimating the intercept, but we are constraining it to be equal. And so in lavaan, you can put a specific value before the asterisk, or you could put a parameter label, right? So if you just put this to 8, then it will fix it to 8. But if you use kind of string variables, I'm using tau because that is a common notation for intercepts. So if I say tau 1, each parameter that has tau 1 in front of the parameter or yeah, in front of the parameter, that's probably the easiest way to describe it. That's going to be constrained to be equal. So I could do tau 1, tau 2, tau 3, and tau 4. That means nothing's being constrained to equality. I'm giving the parameter a label, but I'm not constraining anything to equality. But with tau 1 across all 4 waves, that is constraining the intercepts to be equal over time. So next we will get our fit object, and we are going to be using the sum function uh, because in the growth function, what it does is automatically sets those item intercepts to be 0, and we don't necessarily want that. And because we are going to be fixing certain parameters to be 0, certain parameters to be a constrained to equality, the sum function is going to be make our lives much easier, and that way we are kind of making our lives easier, so we're not because the sum function had and the growth function have slightly different assumptions. 98% is identical, but with the growth function, again, it automatically will set all the item intercepts to be 0, and we don't necessarily want that to be done just yet. So again, that sum function is the one we are going to be using. So that is the unconditional growth model, and we can go ahead and we can run this. And so the first thing we'll do is take a look at our model data fit, and we can see 14 degrees of freedom. We have a pretty decently small chi-square. It's significant, but again, that's not all that substantial. And again, that chi-square test is going to be highly sensitive. And so I really don't pay it too much of attention. Now, if this was 280 with 14 degrees of freedom, I would care much, 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 much more. But we are in good shape here. And essentially what I do is I defer to kind of other fit statistics to really tell me the story. I just kind of take into account the chi-square. Our CFI and our TLI are both 0.99, so we are good to go there. We have our RMSEA. It's 0.04 and it's got a fairly tight 90% confidence interval. So we have 0.018 and 0.061. So we are, again, we're in business there. We are doing a very nice job at replicating the characteristics of the data. So first, we are going to look at our latent variables output. So what I do is I like to look here. Not that it's going to make much meaningful and give you a whole lot of meaningful information, but it's something that you might want to keep an eye on. Is that you want to look at our factor loadings and typically we want them to be above 0.70 and above. That's Lederman and Kenny's 2012 recommendation in their common fate paper. I tend to be a little bit more liberal with it. And the rationale, or part of the rationale, I should say, is 0.70. That means roughly 50% of the variance is occurring at the dyad level. Because if you square those factor loadings, that's the amount of shared variance that the couples have. So if both are 0.70, that means 49% of the variance is at the couple level, at the dyad is shared between partners, and 51% is measurement error and individual and unique perceptions of the construct that is unshared with their partner. And so, again, the idea is you want to have a large proportion of the variance shared between partners because that's the idea of a common fate. Here, since I'm using partner referential items, I feel supported by my partner. I think my partner is warm. I think my partner is affectionate. I think my partner is responsive. That's partner referential items. So the factor loadings tend to be roughly 5 to 10% smaller compared to relationship level questions. Me and my partner are affectionate towards one another. my relationship is characterized by affection, right? So it's not the focus of the items is on the relationship and not necessarily on the partner themselves. So if those items were measured at the relationship level, these factor loadings would likely be far more substantial and closer to that 0.70 threshold. But even so, even if, right here we probably have, um, point 0.60 times 0.64, that's somewhere around 37-38% of the variances at the dyad level or shared between partners. In my eyes, that's still fairly substantial. And we can certainly model that. And I think that would be more than sufficient if our variables, again, lend themselves to a common fate analysis. And so, again, that's something I'm just kind of scanning and taking a look at just to be kind of sure that we're kind of where we need to be. With the intercept and slope, another thing that I typically check for with the standardized loadings, they're not readily interpretable. They don't have a whole lot of meaning in and of themselves, but when we think about all of the parameter estimates being constrained to one in the unstandardized model, that means our standardized loadings should all be roughly the same, right? There's going to be some fluctuation, there always is. Um, so we have 0.88, 0.92, 0.85. That one's getting a little different, and then we have 0.81. And so um, this is potentially saying there's something a little funky going on, that time five is not like the others in some way. So it's something that's not necessarily alarming me, but it's something that I'm actually keeping in the back of my mind. And even though we won't kind of go into it in this video, there is actually something indeed funky going on at time five, and there are lots of errors you get when you try to do more advanced analyses. Like if I tried to run a quadratic growth curve, and I ran into a bunch of negative variances, specifically with time five. So there's some funky things going on there. With the slope, one of the things that I'm looking for is are the difference between the t and t minus one, are those factor loadings roughly the same? So the difference between these two is 0.11. So that's what it is. So here it's, 0.94. So that's a little smaller than 0.11. And here it's, 0.84. So that means it's getting even smaller. And so that tells me, again, there might be something funky going on. And that might even be an indicator that there's actually a quadratic effect. So that's actually what looking at these factor loadings is what actually led me to just try out that quadratic model, because it seems like the contributions of these standardized factor loadings is actually decreasing over time. So again, 0.11, 0.94, 0.84, those are kind of decreasing. So that told me that there might be a quadratic effect, and there wasn't due to again model non-convergence and negative variances and things like that. So you also have covariances. And so you have actually a fairly strong residual covariances here. They are a lot higher than probably you've seen in the baseline common fate model. That is probably for a variety of reasons, but one is that it's the same construct over time compared to the common fate model, where you're actually covariating the residuals of male reporters on construct one and construct two, and those are probably going to be much less interrelated, right? So that unmeasured common cause of unaccounted for variance at the dyad level is going to be different when you're assessing two different constructs. But if you have a single construct, right, its support at both time points, there's probably going to be a lot more kind of shared or unmodeled, or there's going to be like practical reasons why men rate support the way that they do over time. And there might be kind of like a stable component to that. or there might be kind of a common external factor that is stable over time that's accounting for that unexplained variance. And so it is not surprising to see these be zero point 0.4, zero point 0.5, zero point 0.6. That is perfectly normal and is not necessarily an indicator that something is wrong within the model. So what we are going to do here is we are going to look at the intercepts. And so these are going to be the latent means. And so what this is this 14.87. This is the average level of dyad support at wave 2 in PairFam using these data. And we can see that is significantly different from 0. Almost all the time, this intercept will be significantly different from 0, but not necessarily always. Perhaps you might be looking at a construct where you have uh, you have 0 of it at that first wave, but over time, that might you were looking at the development of, is there an increase in the number of units, whatever it might be, over time. So you may actually start out with 0. So like if you want to do like a growth curve on like a kid's allowance, they start off, or the kid's savings, that's probably a better example. The kid's savings, they start out with $0 in the bank. And so if you want to look at the linear change in kids' savings or kids' bank account over time, that intercept is probably not going to be different than 0. That doesn't make it good. That doesn't make it bad. It just means that they're starting out with no money in their bank account, and that's logical and actually makes conceptual and theoretical sense. Um, so we will move on to the slope, and this is the rate of change. So we want this to be significantly different from 0. And so we have a negative slope. All right. So this means that we have a decline in dyad level support over time. So that means that, on average from time 2 or wave 2 to 3 to 4 to 5, the average level of decline across dyads is negative 1.6. All right. So if this is where couples start, to get the estimated mean, you'd subtract 1.64 from this, and then that would be your couple level mean at time 2. And then you do it again and you get the couple level mean at time 3. You do it again, you get the couple level mean at time 4. All right. Over time, this goes from 14.87, and roughly around time 4, this would be much closer to just 14 even, somewhere in that ballpark. And it is significantly different from 0, which is good. So we'll go down to our variances. And so one of the things that we care about is, are there dyad to dyad differences in the sample, in their average rates of change and in their average starting points? So with the intercept, there is a significant amount of variation. So that means there are going to be dyad to dyad differences in the shared levels of support. So how much support is in each dyad member's relationship differs from dyad to dyad to dyad. So some are going to be higher than 14, some are going to be right at 14, some people are going to be lower than 14. There is a distribution of where couples start in terms of the amount of support in the relationship. The problem is that the slope, while the mean is different than 0, we do not have a significant amount of variation, and it's not really all that close. What that means is that on average, within the sample for all couples, there are not couple to couple differences in the mean of the slope. All right. So that means essentially we have 627 couples in this data set. That means this slope right here, this negative 1.64, is attributable to every single dyad in the sample. So if we look at dyad 1, their slope is negative 1.64. If we look at diet 87, their slope is negative 1.64. If we look at, diet 323, their slope is negative 1.64. But if we had a significant variance, what that would mean is, maybe, let's say hypothetically that we actually know each dyad member's slope, which we technically don't, but we're just going to pretend that that's the case. Uh, dyad 74, their slope might actually be negative 164, but dyad 99, their slope might actually be negative 1.3. So that means they're still declining in marital support, in the amount of support in their relationship over time, but they're declining at a less steep rate, right? So their declines are slower compared to other couples. And then you might even have couples, let's say 621, um, their estimate, their slope might be, negative 2.2. So that means that they're declining even more steeply than the average person or the average dyad, I should say, in this sample. So you can think about it is that there are going to be dyad to dyad differences in the rates of change. All right. And so one of the reasons I had mentioned earlier that I'm getting some funky stuff with support and there's some things going on, you want there to be kind of a homogeneous slope, but you also want there to be at least a little bit of variation. But if you are having some dyads actually increase over time, so like you have some dyads that are, 0.164, and then you also have dyads that are negative 1.64, and you have dyads that are, negative 3.28 or whatever that is, then you actually have a lot of variation and you almost have too much variation, and that's where I might actually suggest going into like growth mixture modeling or something to that effect. Because there might be certain couples or characteristics of certain couples um, that are leading them to increase in marital support over time, and there's going to be others that are leading to decreases over time. But there might be these subgroups or these clusters within your sample that change at different rates. Right. So that's where you might want to pursue other analyses. If you have some people changing upwards, some people changing kind of, middle and negative, and some people just absolutely dropping off a cliff. Because what actually can happen in growth curve modeling is these outliers, let's say there's 10 couples who are just on a really healthy trajectory and support is getting better and better and better and better over time. Those folks can mess up a growth model like you wouldn't believe. Even with a sample of 627, those 10 observations can really throw a wrench into things. So you do want to screen for outliers. You do want to plot your means, and really do a really thorough examination of it. Right. All right. So we will also uh, take consider the covariance between the intercept and slope because that can be challenging. So when you're looking at a an association between a predictor or a covariate and the slope, the way I remember it is that if the mean of the slope, so the negative 1.64, and the sign of the association, so if we also had a negative covariance or a negative regression coefficient, if they're both the same, then we know that we're both increasing. So if the mean is positive and the association, the regression coefficient of the covariance is positive, that means we're accelerating at greater rates the higher the level of the covariate, or in this case, the intercept. And if we both have negative, so a negative association and a negative mean, which means there's declines, that means that there's going to be greater decelerations. All right. But either way, the slope is actually getting bigger and bigger and bigger. It's just getting either bigger more positively if both are positive, and negative, getting bigger negatively if both are negative. And when we have opposite signs like we have here, so we have a negative mean, but we have a positive association, that means there's going to be decelerations. That means the slope is going to get smaller the higher and the higher that the association with the covariate or the predictor is, right? So we have a negative mean, or yeah, so we have a negative mean. So that means on average, couples are going down by 0.164. But when they start higher, all right, and the intercept, when this value is higher and higher and higher and higher, that means they decelerate. The amount of support still goes down, but it goes down at a slower rate. So, for instance, let's say, on average, the sample goes down by 1.64. Let's say, you can even test interactions, latent variable interactions using either Bayesian or latent moderated structural equations. You can actually test, again, moderation, and you can imagine like those couples who start at have an intercept of like 16 to start. So it's going to be like 1.13 units higher. Their slope might only be negative 1.4 or 1.3 or 1.2 or whatever it is. So their slope they're still declining, but it's going to be much, much, much less steep. Right. And if we had the inverse is true, let's say this was a positive 1.64 and this is negative 0.95, that means that the marital support is increasing over time, but the higher they start, the slower they increase over time because your relationship can only be so supportive, right? You can only get so much support before you're either in that codependence place and you're like too supportive on one another, or there's only so much support that can happen at a kind of a healthy level, and there's kind of like the ceiling effect that happens, and so again, that makes even theoretical sense. So that is essentially the unconditional dyadic growth curve. And what we can do is also test distinguishability within that dyadic growth curve. And so I have quite literally copied and pasted the syntax from above down here. The only thing I have done is I've constrained residual variances to equality across the waves. So female support those residual variances. So female support, tilde, tilde, female support with a label, that is going to be a variance. And in this case, it'll be a residual variance, uh, is going to be equal to male support at that same wave. All right. So notice at each wave, it's not the same. So we have psi 1, 2, 3, and 4. So there can be wave to wave differences in the amount of unexplained variation in the observed indicators. So essentially everything that's not accounted for by the latent factors and the common fate variables. And so random measurement error, other perhaps predictors, item unreliability, whatever information you kind of want to throw in there. But we're constraining those to be equal across partners, but not necessarily equal over time. And then what we do here is we constrain those residual covariances to be equal. So male wave 2 is residually covariated with male wave 3. And we do the same thing with females, and you can see they have the exact same label. All right. Um, Now, when we testing indistinguishability, we are going to constrain those item intercepts to be equal. So remember, that's how we tested indistinguishability with the baseline common fate model. Well, we are going to be doing that exact same thing with the common fate growth model, where now all of the information about the means from both partners is getting pushed up to the common fate variable, which is then getting pushed up to the slope in the intercept factors. Right. And so that is how you test distinguishability within the common fate growth model. And you'll see down here, the only additional piece of syntax is I have a likelihood ratio test examining the statistical difference. Are we harming the model by imposing these constraints on our variables? Right. So again, we can go ahead and we can run that. And generally, all I really care about when running the unconditional growth model and looking at distinguishability is this chi-square. So this means that because it's non-significant, that we are not harming the model by telling the male partners and the female partners, you are identical in every single parameter in this model. You have the same amount of unexplained variance, you have the same means, you have the same factor loadings, which we've already kind of done by default. Everything is the same. You are not in any way, shape, and form identifiable by any characteristics within the model, and you are essentially interchangeable. So that means male and female, you can switch being dyad member one and dyad member two, and it does not matter. Right. And so the final thing that we'll talk about is looking at predictors of the intercept and the slope, which is what's called a conditional common fate growth model. And so I'm reusing the syntax actually from the first model that we ran, the unconditional model. I did not pull forward the constraints in the distinguishable model, or technically the indistinguishable model. All right, just more for simplicity. But you can certainly do that. That is not a problem whatsoever. Um, and in reality, you would not want to run these analyses because what we are actually going to be doing is we're going to be looking at male and female secure attachment as predictors of the intercept and slope. These are the only new um, parameters that I've included in the model. Other than that, the syntax from the unconditional growth model is identical. The reason that in practice you would not do this is because there's not any significant amount of variance in the slope. So as I said before, the slope is essentially a constant. There's small little variations, but everyone, all the dyads, all the couples are clustered really, really, really close together in terms of the values of their slopes. So there's going to be negative 1.61, negative 1.61, negative 1.62, negative 1.7, negative 1.53. Again, you see there's not a lot of variation there, right? So when there's not a lot of variation, you can't predict variation, which is what we are trying to do with these predictor variables, introducing these covariates. So if there's not a significant amount of variance, accounting for a significant amount of variance, as we'll see, for an amount of variance that actually isn't significant doesn't really mean a whole lot. So it's essentially like, let's say you have two parameters. Let's say there's a non-significant relationship. Your beta is, let's say 0.05 for men and negative 0.08 for women. All right. And both are non-significant. Both p-values are, let's say, are 0.50 and above. You can compare the two of them. You can see whether or not they're significantly different from one another. You can do using path constraints or a walled test, but both are non-significant, so there's not there's not a whole lot of information that gives you. Yes, men and women might be different on those parameters, but neither one of the parameters is actually consequential in the model. So why do we really care about those differences? So again, that's part of the reason that you would not want to use predictors when there's not a whole lot of variation. But I am doing that for demonstration purposes only. So we can go ahead and we can run the model. Again, as I said earlier, these lines 148 to 153 are the only additional pieces of syntax I added into the model following the unconditional model. So what we have is we now have 26 degrees of freedom, and our chi-square jumped up about 75 points, which is really not good. We can see our CFI and our TLI went down fairly substantially. They're both at 0.99 before. And so we can see that there's potential problems with this model. All right. And so our RMSEA, our value was, roughly around 0.04. Now it's jumped up to 0.07, so it's almost doubled in size. Our confidence interval is perhaps even a little bit tighter than it was, but our before we were like 75% chance that our RMSEA was below 0.05. Now it's less than 1%. So we are clearly inducing harm to the model So that is something you'll want to be wary of, and that's something you'll want to think about. And for our model, the reason that that's probably happening is because we are introducing male and female attachment, specifically a secure attachment. And there might be associations between male and female attachment to the observed indicators support at wave 2, 3, 4, and 5, that it goes beyond the growth process. In other words, that the growth accounts for some of the covariation between male and female attachment and each of the observed indicators of support, but it doesn't explain all of it. So there's something else that there's associations between a male and female attachment in each of the observed indicators that's not accounted for by the growth model, which means that potentially our parameters in our growth model are going to be biased, either upwardly or downwardly, because that correlation is trying to get out somewhere. The model's trying to find a way to account for that correlation since we're not doing it in our model. So that is essentially, if you want to learn more about that, that's looking into path tracing rules, looking into model misspecification, and things of that nature. All right, so we will shift down to the output. And again, I'm keeping an eye on the intercept and the slope, their standardized values. And you will see that they change. They are not going to be identical because, again, SEM simultaneously estimates all of the equations. And by inducing or introducing, more specifically, male and female attachment, you are actually adding new sets of equations, and male and female attachment is going to be correlated with or associated with each of these observed indicators. And that's going to ever so slightly change these standardized factor loadings. I believe this was 1.09 or something like that before. Now it's 1.32. And you can see that these others have shifted just a little bit. This went up a little bit as well. So that is to be expected. That's not necessarily a sign of problems. So what we have is we have male secure attachment predicts variance in the slope. And so we are going to pretend, for sake of demonstration, that the slope actually has a significant amount of variance. And so we have a negative mean. So there were declines in support over time. And so what that means is we had a negative mean, and then we have a negative association. That means the higher that men were in secure attachment, the quicker the declines in support. All right. So again, that doesn't make much theoretical sense, but I will tell you that there is, again, problems with support at time 5, which is potentially causing some of these problems that we're seeing. So don't pay as much don't place any interpretive or theoretical value on this. Focus more on the interpretations of it, and focus more on how to interpret these effects properly, because they are, in a way, kind of nonsense parameters due to the model misspecifications that are likely occurring. Females, on the other hand, were not significant, but as we can see, the more women were securely attached, so the higher and the higher they reported on their own attachment security at time 2. That means they declined in marital support at a less rapid rate, at a slower rate. So you can kind of imagine just picking arbitrary numbers out of the clear blue sky as, if, women who are 3 units higher than the mean, than the sample average, let's say their slope was negative, 0.10. So they're still declining, but because they were higher on attachment security at time 1, they're actually declining at 0.10 rather than negative 1.64, which was the dyad average. So we can see that individual level effects can change or potentiate change at the couple level. So this is actually introducing the idea of a hybrid model where we can use individual level predictors like we would use in an actor partner interdependence model to predict change at the dyad level. We can also use common fate variables here. So if we wanted to look at like relationship commitment or relationship quality or dyadic coping or whatever it might be, we could also use a common fate variable to predict the intercept and predict the slope. It does not need to be an individual level variables like you see here. So hopefully this has been helpful in helping you understand the common fate growth model, both the conditional growth model, the unconditional growth model, and testing distinguishability in the unconditional growth model. Thanks for watching.